Okay, so in this example, they give us this function. Let me bring it down here for us. F of x equals 6x to the fifth minus 15x to the fourth minus 50x cubed plus 7. And they want us to find the critical numbers. And so how do we find critical numbers? Well, it's all about the derivative, isn't it? Let's take the derivative. So the 5 comes down. That'd be 30. Subtract 1 from the power. X to the fourth. 4 comes down. Minus, so that's 60x to the third. Subtract 1 from the power. 3 comes down. Minus 150. X to the second. So 1 and the 7's gone. It's just 0. So, okay, so there's the derivative. And we need to set it equal to 0 because the critical numbers are where f prime equals 0 or plus or minus infinity. And the only, you might wonder, well, how's it going to equal plus or minus infinity? That'd only be if you have x to a negative power, then x equals 0 would do it. Because if you have a 0 to a negative power, that would be infinity. Anyway, we don't have that. We don't have negative power, so let's don't worry about it. Let's go ahead. Got to solve this equation now equal to 0. How do we do it? Well, we're going to factor out. Do you notice that all these, what 30 goes into all those, and they all have x squared. So I'm going to take out 30x squared. Okay. And that leaves behind what? X squared, right? Because that I multiply to go back to that. Minus, and then this and multiply to be what? 2x, because that one power would add to go back to that. And then this would be, what's that? 5, just 5. And that would go back to that. Yeah, I don't need that parentheses so far over. Equals 0. Okay, I factored it. Now, let's factor a little bit more. Can we factor what's left? Oh, this doesn't factor. So we stop there for a second and we set each part equal to 0. The first part equals 0 or the second part equals 0. Why is that? Well, because if two things are timesing, right, the parentheses mean multiply, to equal 0, that means logically the first one's 0 or the second one's 0, right? If I said, hey, I'm thinking of two numbers and they multiply to come out 0, how can two numbers multiply to be 0? Either the first one could be 0, 0 times anything can be 0, or the second one could be 0, anything times 0 would be 0, right? So that means that's true for big things or little things. So the first one is 0 or the second one is 0. That's what it means when two things are multiplying to be 0. Okay, let's finish this one. This one's easy. Just divide by 30. Boom. And this one is x squared is 0. 0 over anything is just 0. Okay, and then root it. That's easy. X is 0. Okay, now what about the other side? The other side's not so easy. We're going to need to do it with the quadratic formula. So it's going to be x equals negative b. Oops. Negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, and this is, a is 1, b is negative 2, c is negative 5. So let's plug those in. Here we go. So x equals, and square root of, okay. So negative b, so that's negative, negative 2, plus or minus, right? Because b is negative, formula's got a negative, right? Plus or minus square root of b squared, negative 2 squared, minus 4 times a times c all over 2a. Okay. Um, I'd probably just go straight at this point to Desmos. Let me show you. So I'm going to go straight to Desmos and just type it in. So it's 2, and I'm just do the plus one first, plus the square root of b squared minus 4 times, go back. You notice I skipped the negative, right here. I skipped the negative because who cares? We know it's going to become positive, and double negative made positive there. 4 times 1 times negative 5 over 2. 4 times 1 times negative 5 all over 2 times 1, so just 2. So there we go. 3.44, 3.4494, 3.4494. So there's one answer. X equals 3.4494. Or, now the other answer would be the negative version. So go back, go to the top there, and make that negative. And you get that answer, which is negative 1.4494. Negative 1.4494. Okay, so we got three answers. Zero, the three something, and the negative one something. Three answers to when we took the derivative and set it equal to. Those are all places, those are all x values that will make the derivative zero, meaning they're critical numbers. Critical numbers are places where the derivative is zero or infinity. We don't have any of those because you need x to negative powers to have those. We don't have that. So, all right, so great. So we found three what are called critical numbers. Now, what does that mean? Critical numbers can be, maybe I could write down here. Critical numbers can be max or min or neither. So those are places where you could have a max or a min or neither. So how do we know? Well, that's where it gets a little tricky. You got to do a big number line and you got to do a bunch of work. So let me do that. So I'm going to do a big number line here. Um, move it down just a little bit. Okay. And I'm going to put our spots on them, put them in order. Which one comes first? Which one comes first? I'll put the negative one over here. So negative 1 point. Well, let me do it better. So let's put right here, negative 1.4494, and I'll put 0 over right here, and I'll put positive 3.4494 there. So I'm breaking the number line up into 4 sections. See what I'm talking about? 3 numbers make it 1, 2, 3, 4 sections. So there's always one more section than there are spots, right? You break a stick at one spot, it's 2 pieces. So you break a stick in 3 pieces there, I mean, in 3 places, there's then 4 pieces. So we have 4 sections, okay? And so what I'm going to do is I'm going to get a little more space for us here. I'm going to break these up. Oops, I didn't hold that long. I'm going to break these up into 4 sections, okay? In fact, I might need a little more room on this one. So move this one over. It's just all spacing, right? It doesn't, no, that wasn't good. About that. There we go. All right. So there we go for spacing. So now we're just going to do work. We're going to need to pick, this is a number. This is a number line with 0 in the middle, negative numbers over here, positive numbers over here. So I'm going to pick something in between each of these regions. So what's a number in this section? That'd be like -2. What's a number in here? That'd be like -1. What's a number here? Like +1. Now, I could have done +2, +3. What's a number to the right of 3? Well, like 4, 5, 6, anything. So I'm just picking numbers, and this is a check. I'm going to check at that region, check at that spot. I'm going to check at that spot, and I'm going to check at that spot. So I'm checking in each of those locations between. And what am I checking for? I want to find out if the graph is going up or down or back up, down, what it's doing. As I know these are critical, right? These blue ones are critical. And I'm checking in between the critical values. Checking what? Checking the derivative. Because remember, the derivative here tells me if things are going up or down. In fact, I'm going to use this factored version a little bit easier. So I'm going to check the derivative. Let me bring it down. Let me, in fact, get these out of the way. And I'm going to put the derivative right here. What is it? So again, the derivative right here 30x squared. So let's write that down. So 30x squared. Oh, 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 here we go. 30x squared times x squared. What was it? Minus 2x minus 5. And I'll do a different color for each of these, but I'm just going to keep plugging in. Let's try to vary my color here. And it's a bit of a tedious process. Okay, so I'm going to take the minus 2 and I'm going to plug it in, plug it in, plug it in. All right, I'm going to go back to Desmos. Here we go. So back to Desmos. So it's 30. What did I say I was going to plug in? I already forgot. Look at that. How quick that is. I'm plugging negative 2. 30x squared minus 2x minus 5. So 30x squared. So I'm plugging negative 2. 30 um, times negative 2 squared. 30x squared times, what is it? 30x squared times x squared minus 2x minus 5. X squared minus 2x minus 5. X squared minus 2x minus 5. So squared minus 2x minus 5. Boom. See how I did that? 30x squared times x squared minus 2x minus 5. Whoops. I didn't do that one. I did that. Okay. I plugged in negative 2. What am I getting? 360. Positive 360. So this comes out right here. Positive 360. All I really care is that it's positive. Positive. So let's check the next one. The next one, I'm supposed to plug in negative 1 as my check. This one was negative 2, right? I'm going to plug in, so I'm plugging in it into what? This is the derivative. Remember, this is f prime I'm plugging into. F prime equals f prime. It's the derivative, not the original function. It's the derivative. So I'm going to plug in negative 1 now. Let's go back to this, plug in negative. So everywhere we have negative 2, I'm going to make it negative 1. Well, negative 1, negative 1, all those parentheses, negative 1. Boom, what do I get? Negative 60. So I come back, okay, that one's negative 60. All right, next one. F prime will equal, this time I'm plugging in positive 1. Plug it in, plug it in, plug it in, positive 1. I'm checking. Plug in positive 1. Okay, so get rid of that negative. Positive 1, positive 1, positive 1. What do I get? Negative 180. Negative 180. And then last one. Now I'm plugging in 4. Plug it in, plug it in, plug in. Find out that F prime when you plug in 4, we're going to get, make that a 4 now. 4, 4, 4. 1440. Positive. 1440. Okay. So what in the world does all this mean? Here's what this means. This means the graph we're talking about is, what does it mean when the first derivative, remember the derivative is the slope. So if the slope is positive, it's going up. And if the slope is negative, it's going down, going down, going up, right? So a general look of the graph's going to start here, go up in this section, then go down in this. Well, here, let me do that. Not quite so dramatic. So go up, go down, go further down, and then go up, right? What I did there, it's going up. The first derivative is positive. In this section, I so these blue points I found are critical spots, and now we can see what they are, right? This right here is a max. That means this critical value is a max. He's a local max at L max, local max, and his he's got a miss. How do we know? Well, because we found out we took the derivative, the first derivative, and we plugged in something to the left of him, negative 2. Could have plugged in negative 3, negative 4, negative 5. It's all good. And it came out positive, which means the derivative in this whole region is going up. Now we know the derivative is 0 right here. Then we plugged in something between these two, like -1. We plugged in negative a half, negative 0.5, whatever, and it's going down. So this must be a max. And then we plugged in here, and it's going down, and it's going up. So this one right here, this has got to be a local min. So local max, local min. So this one is a local min, isn't he? That could be, and this one right here in the middle is neither. He's neither a local min nor a local max. How do I know? Because it was going down beforehand and went down afterwards. Well, then why did the derivative become 0? It does that sometimes. It's um it's actually going to end up being a what we call a inflection point. We'll learn about that later. It actually changes concavity if you're interested. Here, I'll draw it a little more accurately to show you. It actually means that the graph is actually just like this. It's going down like this, and it shifts. It's still going down, but it shifts concavity there. See how it's concave down and then concave up? Like that, it shifts. So that's generally what the graph is doing between those values. That's what we're figuring out. Hey, it's good to see that this is true. Let's as we wrap up this video, let me show you 6x to the fifth. I'm writing it down real quick on my paper. Minus 50x cubed plus 7. Let's go to the Desmos grapher. I still have that online. Yeah. I'm going to go to desmos.com, the graphing tool, and I'm going to put up here y equals, I'm just going to put that function, our original function, 6x to the power 5 minus 15x to the fourth, so minus 50. This is our original function. Just trying to graph it as I go. Minus 50x cubed. Hold on, Desmos. You're a little too quick. Minus 50x cubed plus 7. All right, there it is. There's our function. Now, what did we say? Let me make this, if I can, a little bit smaller. Here, let me get this out of the way. Okay, so I can shrink it a little bit. It's kind of hard to see the whole thing. But yeah, it's hard to see this. Let me shrink it down and then widen it a little bit. Shrink it down, widen it. I'm not sure this is I'm really not accomplishing a lot, am I? All right. I Okay, it's a little better. I like that. Hey, there we go. Now I'm getting somewhere using two fingers. Yeah. Okay. There's a nice little look at the thing. Put the equation back on the screen. There it is. So notice that so it's like we said, do you see here? Let me make it just a little bit like this, like that. And maybe just a little wider. Let me see. It's pretty good. Okay. Um, right. Boom. Let's bring it over here. Let me draw on it. Let me show you. Run it over so I can draw on it and highlight a couple things just to show you that we have found what's true. I'm showing you that our derivative work has led us to a lot of truth. So here's the graph. Okay. Look at this. So what did we say? Oh, here it is. We said the graph is going to go up, down, and then up. And this would be negative 1 point something, 0. Let's find it. So notice this right here, negative 1 point about 5. So that'd be right around, right around here. Sure enough, see, this looks like a max, huh? Right? It's going up before that. See, it's going up before that. Hits that 1.44 whatever number, then goes down all the way to 3.5. Then goes down, shifts concavity right here. See what I talked about? This is a shift in concavity. See how it's concave up and then concave down, but it still keeps going down all the way to there, which is what? 3 point something. See that? Right there. That's got to be our 3.449, 3.4494. And that's a min, isn't it? It's a local min. This is a local max. Then it goes up, up, and away after that. Up, and away after that. This one was negative 1.4494. Negative 1.4494. Look at that. Beautiful. Look at the power of calculus, right? We were able to figure out generally what that graph looked like by using derivatives. Do you see? This is where you start to feel the power of calculus. It shows its might, and that's right. How do we do that again? What did we do? We first off we took the original function, we took the derivative right here, and we set it equal to zero. Why? We wanted to find the places where the derivative is zero. Those are critical numbers. Those are places where you're going to find your maxes and your mins and your inflection points, it turns out, with concavity changes. Then we factor to solve it equal to zero, we had to factor it. Set the first part to zero, that was just x equals zero. Set the second part to zero, and we used the quadratic formula, found those other two answers, right? And then we put those three answers on the number line and we checked values in between them plugging into the derivative, the first derivative again, because the derivative tells us the slope. If the slope is positive, the function's going up. If the slope is negative, function's going down. Negative, down. Positive, back up. And that told us the max, the min, the change in concavity. And we did the real graph on Desmos, and sure enough, we got it. And so the power of calculus. There we go.